Hey there, I'm Adam Gilbert, Associate Professor of Mathematics at Southern New Hampshire University. Welcome back to my channel. Today in the Statistical Learning and Classification series, we'll be talking about performance metrics for classification models. We'll start by having you open up or copy the Quarto document for this discussion. So if you navigate through the course webpage, there's in row 7 of our course timeline, regression versus classification and performance metrics for classifiers. I'll have you click on the link to the QMD file, and I'll add this link to the description underneath the video for those who aren't actually in the course. What we'll do from here is I'm just going to have you copy and paste the entire existing Quarto document. So we're going to copy and paste all of the lines of code here. We'll move them into Quarto, and then we'll work from there. So with that copied, let's head over to RStudio. I am in my project for this course. I'm going to go to File, and New Quarto document. And I'm going to create an empty document and get rid of even the little bit that's provided there as a default starter. And all we'll do is we'll paste in the markdown that we copied from GitHub. And so now you should have a notebook titled Assessing Classifiers. We'll go to File, we'll save this so that you have access to it and so that we can render it. So I'm just going to save it as Assessing Classifiers. And then I'm going to render it. I'm just going to render it so that there's some math in here, so some mathematical formulas that might be beneficial for us to see in the actual rendered version of the notebook. But what we'll do for the most part today is we'll play around in the actual Quarto file. So we'll start by loading the tidyverse and loading tidy models. I'm on a Mac, so I'm going to do this by holding down Control and hitting Return. If you're on a Windows computer, you can hold down Control and hit Enter. So I think I misspoke. I'm on a Mac and I'm going to hold down Command and hit Enter. So the tidy models and tidyverse meta libraries are loaded now. And what we're going to do is we're going to just build some toy data. This just means fake data to play with. I have a large code cell here. This large code cell contains a bunch of different toy data sets that we can play around with. And I'll encourage you, we won't go through them all in this video, but I'll encourage you to come through and see what you can do with the other data sets, play around with them. They're pretty interesting. We're going to start with an easy two-class case. So we're going to have 25 observations in our first class. We're going to have 30 observations in our second class. The X and Y locations of these observations are going to be randomly generated. And we're going to package the X and Y locations along with the class of the observations together into a tibble. And you might remember that a tibble is what the tidyverse ecosystem calls tables or data frames. Now that data set is loaded up for us, we can see it in the global environment. We're going to scroll down into this next code cell, which will just plot the data for us. So I'm going to run that, and we can see now that we have a classification scenario here where we've got class A, which is these pinkish dots, and class B, which is the bluish triangles. And what we want to do is we want to build a classifier, or maybe a set of classifiers like we'll do here, to separate the pink class from the blue class. And we'll do that with a couple of classifiers. So first, I've got a decision tree. This code should look familiar to you. This is using the Tidy Models framework. So we start out with a model specification. I think in class, instead of calling this DT-CLF for classifier, I've suggested we call it DT-spec for model specification. This keeps consistency. So I'm just going to change it to spec. And I'm going to run that. So we're building a decision tree. The engine to fit the tree, so the mathematics or the algorithm behind the scenes here is going to be R part. So that's a package in R. It stands for recursive partitioning. And then we're going to set the mode for the decision tree to classification, because this is a classification problem. We have a recipe now. Recipe determines the formula for how we're going to make the classification. So we're predicting class using the X and Y location of the observations, and R will be able to find the data in that toy data frame. You'll notice that we're not splitting data today into training and test sets. We're not using cross-validation or anything. And that's because the purpose of this video is just to explore different classifiers and to take a look at performance metrics. So keep that in mind, that we are skipping those steps here. So we've created our recipe. The next thing we do is we package our model and our recipe together into a workflow. So I'm just going to change CLF to spec. You don't need to make those changes in this notebook if you don't want to, but if you want to make this look a little bit more like what we've discussed in class, changing CLF to spec will match with what we've discussed. So we create a workflow. A workflow just packages our model and our recipe together into a single object. So we have DTWF, and then we can fit our workflow to the toy data. Again, generally what we would do is we'd fit to the training data, or we'd run cross-validation, or even maybe tune our model instead. But for today's purposes, fitting the model is what we want to do, because we want to get, again, to performance metrics. So we'll fit our model to the data. What we're doing here is we're creating sort of a mesh, a grid of points that we can classify. The purpose of this, we'll see when we draw a picture, is just basically going to be to paint the background of the feature space, the region over which our points lie. So we're creating new data, and then we're augmenting new data with our model's predictions. So you might remember how augment works. It takes the original data frame and it adds a few columns to it. One of those columns is a class prediction. And from there, we'll use ggplot to draw a picture. So we're going to plot our mesh grid. So we're going to paint the background here. And then on top of that, we're going to plot our original data points. So we're going to plot the points that we were trying to classify. And over the painted background, we'll be able to see how well our classifier did. And then we're giving some labels just for convenience. So there is our classifier. And as expected, this has, at least visually, done a pretty good job. So all of the blue points are falling in the blue region. All of the pinkish points are falling in the pink region. And you'll notice that the classification boundary is a vertical line here, and that's because decision trees ask yes or no questions, resulting in decision boundaries that are perpendicular, so they meet at a 90-degree angle to our feature axes. So it looks like this decision tree has simply just asked whether the X location of an observation in our data set is more than about maybe 33 or 34. We'll do the same thing. I'm not going to change the CLF suffix here to spec. I'll just leave it alone. But again, in class, if you are in my class, we talked about model specifications, and that's what this is. So we're creating a new type of model here. It's a nearest neighbor classifier. We're going to use 3 neighbors. The engine that we're going to use for the mathematics with this algorithm is KNN, and the mode that we're using is classification, again, because we're working on a classification problem. The rest of the lines in this code cell are pretty much the same as what we saw in the decision tree cell. So I'm just going to cruise through here. We're creating the recipe, packaging the model and recipe together into the workflow. We're fitting the nearest neighbor model to the toy data. We're creating that background mesh grid. We're augmenting the mesh grid with the model's predictions, and then we're plotting so that we can see the decision boundary and the original data points. And so again, with the k nearest neighbors model, we have, it looks like visually, perfectly classified all of our training observations. So all of the pink observations are in the pink region again. All of the blue triangles are in that blue region as well. You will notice, though, that the shape of the decision boundary is now different. With the decision tree, we had a vertical boundary. Now we have a slanted boundary, and you'll notice that it's not a straight line boundary. So there's this dip in here. The way the nearest neighbor model is working is for any point in space, it identifies the 3 closest training observations, and those 3 closest training observations vote. And majority wins. So the 3 closest training observations to this region in space, at least 2 of them are blue, and the vote then goes to blue. We'll talk more about nearest neighbor models later in our course. But again, a different model led to a different decision boundary. In this case, both models classified perfectly because it was an easy classification problem. The third model that we'll look at is only appropriate for the 2-class classification case, so binary classification. It is the first model class that we will spend significant time on during our semester. So it's logistic regression, but for today, we're just going to build the model, we're going to look at the decision boundary, see what happens. So again, model specification. We're not setting the engine here, the default engine is fine. We're creating a recipe, we're packaging the recipe and the model together into a workflow, we're fitting the model. You'll notice that we're getting a warning here. That warning is indicating that essentially the classification problem that we've given is not difficult, and there's some uncertainty in the model because of that, because lots of different decision boundaries actually work equally well here. So there's some uncertainty about whether we have the right decision boundary or not. And then again, we're creating that background mesh grid that we can paint over. We'll augment that mesh grid with our model's predictions. So this is using the logistic regression model to make those predictions, and then we'll plot. And so here, again, we get a slanted boundary. You'll notice, though, that this one is also different than the nearest neighbor model was. This is a straight line, even though it is slanted. And the warning that we were getting is, again, because we could move this straight line to the left or to the right a little bit and still have perfect classification. And so the decision boundary isn't like uniquely determined. So there's some significant uncertainty here as to whether this is the right location for that boundary or if it's not. All right. So again, what we've noticed is that different classifiers make different decision boundaries. They're shaped differently, they make different assumptions about the data, and they make their classifications differently from one another. What I'd like to do now is just talk a little bit about assessing classifier performance. One way that we can assess classifiers is through accuracy. Accuracy is just the proportion or percentage of predictions that your classification model gets correct. It's sort of the most natural performance metric. It's the one that comes to mind first. What we'll do is we'll work with the decision tree. We will augment our toy data. So we're going to take our training data, we're going to add predictions to it. We'll remember that the toy data has the actual classes for the observations, and once we've augmented, it also has the model's predictions in a column called .pred class. The conf_mat function is from the yardstick package that is part of the Tidy Models ecosystem. This will create something called a confusion matrix, which will list out the actual classes of the observations and the predicted classes of the observations together into an array. And it will show us how often we got predictions correct for each class, how often we got predictions incorrect for each class, and where our model was confused. So let's build that confusion matrix here. So you'll see that the predictions are along the rows. So here's the row where I predicted class A, Here's the row where I predicted class B. And then the actual classes are along the columns. So the first column represents observations that were truly class A, and then the second column represents observations that were truly class B. And so you can see here, not a surprise, we got all of the predictions correct. The accuracy metric just sums over the diagonal. So I have 25 and I have 30. Adding those together gives me 55. So I got 55 correct predictions. And then if I divide that number by the total number of predictions I made, that will give me the accuracy rate for my model. Here I made 55 total predictions, so the accuracy rate is 100%. Tidy models will, one of the packages within Tidy Models will compute accuracy for us, so we don't always just have to look at the confusion matrix and calculate it by hand, but we can, and often viewing the confusion matrix is quite insightful, if nothing else because it shows us where our model makes mistakes, what classes our model is most likely to confuse. But here, we'll compute accuracy. We know what we're going to get. It'll be 100%. So we're starting with our decision tree, the fitted version of it. We're augmenting our toy data. That is going to make, it's going to add columns to the toy data. One of those columns will be the model's predictions, in particular the predicted classes of the observations. And if we calculate then the accuracy, we get, again, no surprise, 100% accuracy here. What I'd like to do is I'd like to switch the data set that we're working with because this one was a nice, easy introduction, but quite boring to work with. And once we switch the data set that we're working with, let's refit our classification models and then take a look at those models' accuracy rates and perhaps motivate why some other performance metrics are necessary. So I'm just going to scroll back to the beginning of my notebook here into that first code, or I guess the second code cell. The first one just reads in the libraries. I am going to comment out that first easy two-class data set. There are keyboard shortcuts for this on my Mac. I'm going to hold down Control, Shift, and C to comment. On a PC or on a Windows machine, I think it's Control, Shift, and C to comment. That same combination will uncomment as well. So I'm going to grab this second separable two-class with a rare two-class case with a rare class, and I'm going to uncomment that, and I'm going to run this code. So this is going to replace my existing toy data with a new toy data set. And let's plot it and see what we're up against. So go back down to the plotting cell and we'll replot. And now we have more observations here, lots and lots of blue ones, and then sort of a rare collection, but clearly belonging to a particular region in space of these pink circles. And so our goal again is to separate the pink circle observations from the blue triangles. Let's see how well our models do. So again, we'll start with a decision tree. We won't walk through the code this time. It's the same as it was before. We create the model specification, the recipe, package the model and recipe together into a workflow. We'll fit the model to the toy data. We'll create that mesh grid to paint as the background. We will augment that mesh grid, so that's adding predictions to the mesh grid that we created, and then we'll plot. So we're plotting the background, and we're plotting the original toy data observations on top of the background. And we can see that our model, our decision tree, has done pretty well. It seems to have carved out a rectangular region here and allocated that rectangular region to the pink class and left everything else to the blue class. So it seems like the decision tree has done pretty well visually here. We'll calculate the performance metrics to verify that numerically later. Let's try again with the nearest neighbors classifier. So again, create the model specification, create the recipe, package the model and recipe together into a workflow, fit the workflow to the data, create that mesh grid as the background that we can paint, assign the painted colors through augmenting to that background mesh grid, and then plot. And we can see here, again, the nearest neighbor model has carved out a region in space and assigned it to those pink observations. It seems to have done visually a pretty good job as well. And now let's skip to the last model. So the last model was that logistic regression model. We'll create the model specification, create the recipe, package the model and recipe together into a workflow, fit the model, create the mesh grid background, attach our model's predictions to that mesh grid background, and then plot everything. And we can see the colors have switched here, sorry for that. But what were those blue triangles in the background have now switched to pink. It's just because there was only one predicted class here. I apologize. But you can see that now the logistic regression model has just assigned everything to the triangle class. And it's assigned nothing to the blue class. It's basically just given up on those observations and said, hey, there's not many of them, and I can be pretty accurate if I just predict triangles all the time. And so we have two models that have done pretty well, and then this last logistic regression model seems to have maybe not done so well. So let's take a look at the confusion matrix. We'll start with the decision tree, but then we can add we can take a look at the confusion matrices for the other models as well. And so here's our decision tree. We have, again, more observations now. There were only 16 Class A observations, but our decision tree got them all correct. And there were 984 Class B observations. Those were the triangles, and our decision tree also got those all correct. So this is a model that has 100% accuracy again. If we look at the nearest neighbor model, so I'm just going to copy that code and use KNN fit as my model to make predictions instead. Same thing. So the nearest neighbor model is also 100% accurate. If we look at the logistic regression model, I should just copy and paste and change the model that I'm using to the logistic regressor. Now we can see that the model is not getting everything right anymore. In fact, what we saw visually is what we're seeing here in the confusion matrix. The model gave up on the Class A observations, it gave up on those circles, and it just decided that everything should belong to the triangle class. And so this model no longer has a 100% accuracy rate. This one has, if we calculate the sum along the diagonal, 0 plus 984, and we divide by the total number of predictions we made, I'm just going to add up all of the values in the confusion matrix, 0 plus 16 plus 984. Again, just so you can see that we're adding up all of those entries to get the total number of predictions. If we run that, we get 98.4% accuracy, which seems pretty great. The other models had 100% accuracy, but this is not a whole lot worse. However, if we really do care about being able to identify those circle observations, then this logistic regression model did really, really poorly. And we want some way to communicate that. And so that motivates some other performance metrics as being necessary. So we do have other performance metrics. Those other performance metrics will tell us how well we are able to identify a particular class that we're interested in, or once our model makes predictions, how trustworthy those predictions might be, especially for a particular class of interest, like perhaps these circles are. And so I'll introduce those other performance metrics. We can talk about them a little bit, and I'll show you how to compute them in R. So again, we can see that the logistic regression model, there it is again, showing you the confusion matrix, and then using R to compute accuracy. This is just going to do the same calculation that we did by hand recently. We get 98.4% accurate. Again, that seems excellent, but our model has just sacrificed all of those Class A observations. It's predicting everything belongs to the triangle class, nothing belongs to that circle class. And really, if we do care about the circle class, this is an awful model. So we have other options available to us. So recall. Recall describes our model's ability to identify observations that truly belong to a class of interest. So if we're interested in Class A, those circles, how well does our model do at flagging observations that really do belong to that particular class? To compute the recall rate, what we'll do is we'll look at the column of the confusion matrix corresponding to the class we're interested in. So I'm just going to bring back the confusion matrix for that logistic regression model. And so if we really are interested in Class A, here's the column corresponding to Class A. I have 0. 0 times where the observation really belonged to Class A, and I predicted Class A, and then 16 times where the observation really did belong to Class A, but I assigned it to Class B. The way this works is the total number of observations that we're looking at is the total number of observations belonging to that column. So here there are just 2 entries that we have to worry about. So there's 0, it's the top left entry, and 16, which is the bottom left entry. And out of those total true Class A observations, I want to know how many I got right. So I'm going to look at the diagonal entry there, and I'm going to put the diagonal entry on the top. So 0 out of 0 plus 16 gives me a 0% recall. What we'll do here is we will calculate the recall rate for those Class A observations. So we're going to switch this to first class, I believe. So we're going to take our logistic regressor, we're going to augment our toy data, that's going to add predictions to it, and then we're going to calculate recall. The true classes are in a column called class, and our model's predictions are in a column called pred class, and the event level that we're interested in is the first one. So we're interested in Class A. R is going to go by alphabetical order here. And if we run that, we get a 0% recall rate. If we switch to the second level, I believe that should take us to Class B, and then we should get 100% recall there. Again, taking a look at the confusion matrix for Class B, we'd take a look at that second column. On bottom of this fraction, we'd have 0 plus 94. And then on top, we'll put, 0 plus 984. And then on top, we'll put the diagonal entry from that column. So that's 984 there. And if we calculate this, we get the 100% recall for that class. So there is recall. Recall, again, deals with our model's ability to correctly flag observations that truly belong to a particular class. So we get the true class correct. An alternative metric is precision. Precision will try to measure how trustworthy our model's predictions are. So once our model has predicted that an observation belongs to a particular class, what is the likelihood that that observation actually does belong to that class? So here, instead of looking at columns in the confusion matrix, we'll look at rows. So we can calculate the precision rate. Let's do this by hand first, and then we can use R to calculate precision for us. I'm going to start again with the logistic regression model because that's the one that is making some mistakes here. So We'll take that logistic regression model, we'll augment our toy data set with predictions. That again just adds columns to the data set. The columns that it's adding correspond to predictions made by the model. One of those columns is the predicted outcome class. The confusion matrix now that we're building compares the actual class to the predicted class. And we'll run that. We see the same confusion matrix as we have been seeing previously. Now, for class A, our precision rate is going to be undefined. Again, we're looking at once our model has predicted a particular class, how trustworthy are those predictions? For class A, our model never predicted class A, so we'd have a calculation that looks like this. The total number of times my model predicted class A was 0 plus 0. And then the number of times the model correctly predicted class A was 0. So this is no good. Precision is undefined for class A here. We'll look at some different examples where we have an ability to calculate precision. But if we look at class B instead, our model did make some predictions where the observations belong to class B. It made lots of them. So in total, there were 16 plus 984 times. And then if we look at the diagonal entry in that row, so that's the entry along this main diagonal, it's 984. So I'm going to take that 984 and put it on the top. And if we calculate, we get 98.4% precision. So if our model has predicted that an observation belongs to class B, then there's a 98.4% chance here that observation really does belong to class B. If we calculate the precision using R with the precision function, again using the second event level, class B, because precision is defined there, we should see 98.4%. Cool. And so we do see that same value. If we tried the first level, let's see what happens. We get missing because, again, in that case, precision was undefined because we never predicted that an observation would belong to class A. All right. Beyond precision and recall, there's two more metrics that I want to talk to you about. The first one is area under the curve of the receiver operating characteristic or receiver operator curve. This compares our model's ability to flag observations as belonging to a class of interest, so to pick out true positives, relative to how quickly we pick up false positives. And so the way this is going to work is we're going to arrange our model's predictions in order of certainty after we define a class that we're interested in. So we're going to pick out the most certain predictions first, and then we're slowly just going to accumulate predictions and track how many predictions were correctly assigned to the class that we're interested in versus how many predictions were incorrectly assigned to that class of interest. We're going to draw a plot to visualize this. The plot is going to have a 45-degree line that corresponds to random guessing, so just randomly assigning observations to the two classes. And then hopefully our model does better than that. If it does, we should see this ROC curve stretching up towards the top left corner of this plot. So let's see what we end up with. Here we are. So we can see with, this is the logistic regression model. This is the one that is making some mistakes. Our model is actually really certain about some wrong predictions. So the most certain predictions are wrong. But then eventually I start making some correct predictions. And it looks like I catch my correct predictions pretty quickly. And I'm eventually then, after I've assigned all of the the observations that I'm most interested in as belonging to that class A. Eventually then just all of the remaining observations belong to class B, so I'm just getting false positives. The area that I'm interested in is the area really underneath this solid black curve. The closer the area is to 1, the better. So a perfect classifier would just shoot straight up here to this top left corner and then shoot straight across. So we'd have a square. The square would have a base length of 1 and a height of 1. So the area of a square with side length 1 is 1 in total. Random guessing would be the area underneath this 45-degree line. That area would be 50%, half. So basically, we want to see area underneath our curve greater than half, and hopefully a lot greater than half. If we see area under this curve less than a half, that means something has gone wrong. Perhaps we have mislabeled our classes, but our model is doing worse than random guessing if we see that. So what we'll do is we'll calculate now numerically instead of looking visually at the area under that ROC curve. We will calculate the area numerically and see where we're at. And so the area underneath this ROC curve is around 0.83, which indicates pretty good classification accuracy. But again, this is with Class A, which we were doing, I misspoke. This is not with classification accuracy. This is with the certainty in the predictions for our models. So our model is picking up Class A observations. It's assigning them higher probabilities than Class B observations fairly often. So it's getting true positives, true positive meaning, hey, I think this belongs to Class A, and that being correct early on with high probabilities or higher probabilities, as opposed to incorrectly saying, hey, I think this observation belongs to Class A, but it really belongs to Class B. All right. I'm going to skip the other classification metric for now because it's not, I didn't put much about it in here. I didn't calculate it in here, but it is one that we are going to use. You're going to use it for your Kaggle competition on predicting price ranges for homes. So we'll talk about that just briefly before we close out the video. But I want to run through all of this again with another scenario. So we'll go back to the beginning, to that second code cell, and we'll comment out this second separable to class with rare case. So I'm going to do that again with Command, Shift, and C all at once. If you're on a Windows machine, I think Control, Shift, and C will work there. Let's take a look at the non-separable 3-class case. So I'm going to highlight all of that. What I should point out is all of the new data sets in this notebook start with 3 hashtags. So you see the 3 hashtags there. That's indicating that I have a new data set beginning. And then the next set of 3 hashtags indicates that the next data set is beginning. So I'm going to grab all of those lines between those sets of 3 hashtags. I'm going to hit Command, Shift, and C on my computer, but if you're on Windows, you'll hit Control, Shift, and C. And then we'll run that code to create, again, a new data set. This data set is going to have 3 classes, though, instead of just 2. And let's see how our models do this time. The logistic regression model we're going to avoid because it's not suitable for more than just 2 classes. So we'll only look at how the decision tree and nearest neighbor models perform. And so here we are, we've got the 3 classes, the green triangles, the pinkish circles, and the blue squares. Our goal is to separate them into classes by assigning regions in this space as belonging to the green group, to the pink group, or to the blue group. We'll build the decision tree. Let's see what happens. So we build the specification, the recipe, the workflow. We fit the data, we fit the model to the data. We create that background. We're going to add predictions to the background, and we're going to plot everything. And so here's how the decision tree does. And the decision tree has allocated 3 regions in space, so anything with a large y coordinate is predicted to belong to that green class. Anything with a small x coordinate and a relatively small y coordinate is predicted to belong to the pink class, and anything with a large x coordinate and a small y coordinate is predicted to belong to the blue class. But we can see that sometimes this model is making mistakes. So it's not a perfectly accurate model. And we wouldn't be able to get a perfectly accurate model here anyway, unless we were severely overfitting. We can build a nearest neighbor classifier as well. So we'll build that specification, the recipe, package them into the workflow. We'll fit the workflow to the toy data. We'll build the background. We'll add predictions to the background, and then we'll paint the background and add the original observations on top of them. And you can see how the k-nearest neighbor model fit the data. And you can see that the nearest neighbor model perhaps has done some questionable things, like assigning this island of red here between the green class and the blue class. So we might question whether this really should be territory belonging to the pink class or not. So perhaps this model is overfitting, but that's a topic for another discussion. Again, logistic regression, we're going to skip because that particular model class is not appropriate here. So we'll get rid of that. And we'll take a look at assessing classifier performance. We'll look at the decision tree. So the decision tree here, now we have a 3x3 confusion matrix. So again, the rows correspond to the predictions. So there are 22 times that my model predicted class A, and the observation truly belonged to class A. There were 4 times where my model predicted class A, but the observation was actually class B. And there were no times where my model confused class A and class C. Similarly, there was 1 time where my model predicted class B, but the observation actually belonged to class A. There were 35 times where my model correctly identified class B, and 1 time where it confused class B with class C. So the observation really belonged to class C here, but my model predicted class B instead. And then for class C, 2 times where I predicted class C, but the observation was truly class A. 1 time where my model predicted class C, but the observation was truly class B. And then 29 times where my model predicted correctly. So you can see the largest numbers are along the diagonal. Generally, that's pretty good. That's indicating that our model is making correct predictions. If we wanted to compute the accuracy for this model, we can. Again, by hand, all we're doing is we are adding up the correct predictions. Those are the ones that appear along the diagonal. So the 22, the 35, and the 29. And then we're dividing by the total number of observations we made predictions for. I'm going to cheat a little bit, and I'm just going to look at my global environment, find my toy data, and identify that there were 95 observations there. So we must have made 95 predictions. So this total divided by 95, we get about 90.5% accuracy. If we wanted to make that same calculation with our functionality, we use the accuracy function. Accuracy, gotta spell it right. And then we pass the truth, so the correct classes, so that's in the class column, and our model's predictions. So .pred class is the column that augment will add. And if we run this, we should also get 90.5. And so there it is. So same answer 2 different ways. If we took a look at the nearest neighbor model, again, here is the confusion matrix. That one has, it looks like 100% accuracy. There are no values off the diagonal. Again, we want to be careful about this though, because these are predictions on the training observations. So my model knew where these observations lived and what their classes were ahead of time, it's perhaps no surprise that this model is performing so well. But given the picture that we saw, we probably don't expect this model to do as well on future observations. There are some questionable things happening with the class assignments and with the regions that are being allocated to different classes here. Again, with these models, logistic regression is not viable here, but we could compute our other performance metrics, so not accuracy, but recall. So again, we could take a look at the confusion matrix, not for the logistic regression model, but let's take a look at the decision tree, because that one is the one that has been making some mistakes. For recall, we're looking at columns in my data set. Let's for a second say that we're interested in class A. So if we're interested in class A, I want to know about all of the class A observations in my data set. So the true class A observations, there were 22, and 1, and 2. And out of all of those true class A observations, we got 22 of them predicted correctly. 22 over 22 plus 1 plus 2. And so we get 88% recall for class A. Let's verify that we can replicate that number with the recall function in R. So dtFit, augment the toy data, use the recall function. The event level that we're going to be interested in here is the first one, because A comes first alphabetically. And we should, again, get 88%. And we don't. I should have known this. The reason for that is because with recall, the way Tidy Models is calculating it, it's aggregating over all three of the classes. So it's calculating a sort of weighted recall measure. So it's accounting for all three classes and indicating that we care about all three classes there. I don't remember how to get this recall function to pay attention to only one class, and I'm not sure if it's possible or if we would have to refit our model as a binary classification model, class A versus all of the other classes. But that, I don't think we need to worry about that here. What we can say though is the recall function here is calculating a weighted recall measure where we do care about all three classes and not just one of them. If we did only care about one, then reframing this in terms of binary classification does make some sense. All right, and then with precision, Tidy Models and that functionality will do something similar. So I won't calculate precision by hand. Instead, we'll just do it with the functionality from Tidy Models. So, we don't want log-reg fit, we want dtFit. Again, here's the same confusion matrix. With precision, we care about rows instead of about columns, because we care about once our model has made a prediction that an observation belongs to a particular class, how trustworthy is that prediction? We can do dtFit here. The precision and recall function, I do not think take the event level argument because, again, they do that weighted averaging. And so here we are, precision weighted over all three classes is around 90%. All right. ROC AUC usually is for binary class, so I'm going to leave that out here. We're typically comparing true positives and false positives, so that requires that we have the ability to say what a positive is and is not. So having two classes there is better. I do know that there are ways to calculate the ROC curve and to produce the ROC curve for the multi-class case, and I might do another video on that later on. Let's leave this here, I think. What I'm going to do is just bring you back to the top of the notebook and point out that There are lots of data sets that we did not take a look at in this video. I just feel like it's gotten plenty long at this point. So there's this other 2-class rolled data set. There's a data set called a Swiss roll, which is a relatively famous data set. It's something that people will use to test models against because of its particular structure. So this is a 2-class Swiss roll, but then I have a 5-class Swiss roll that you can play with. So that is, again, taking a look at those 3 hashtags in a row. Here are the lines corresponding to the 5-class Swiss roll. I've got another data set, 5-class concentric ellipses. This one I'll just uncomment, create, and plot for you so that you can see what that data set and classification task might look like. So here's a differently organized collection of classes that you can explore how a decision tree, a nearest neighbor model, a decision tree or a nearest neighbor model perform on this particular structure. Again, the logistic regression model won't be appropriate here because it's only useful for 2-class case. There are ways to adapt it to be appropriate for a multi-class classification, but we won't do that in our course. All right, so please do play around with those other data sets. I hope you find them interesting, but for now, I'm just going to do one more thing before I close out of this video. I hope it has been at least moderately useful for you, but one more classification metric before we close out. And again, instead of looking at this in the actual markdown, I'm going to bring us into the actual rendered HTML document. So for your Kaggle competition in our course, the performance metric that you're going to be using is not one of the ones that we talked about in this notebook. The performance metric will be something called multi-class log loss, which is a performance metric that cares about how certain your model is in its predictions. The formula looks kind of scary. The 1 over n here is taking an average, so we can think of that way. This first sum is summing over all of the predictions that have been made, so summing over all of the rows in your data set. The second sum is for each row, I'm looking at all of the different classes that the observation could belong to. This Yij is either a 0 or a 1. It's a 1 only if the observation in row I corresponds to class J. So basically you can think of the term as being turned on if I'm looking at the correct class. The Yij value is 0 otherwise, so no terms other than the term corresponding to the correct class will contribute to this multi-class log loss for any observation in your data set. And then this logarithm piece is dealing with your predicted probability. So Yij hat is your model's predicted probability that the observation in row I belongs to class J. And so the idea is, if we're looking at the correct class and your model was very certain that that observation did belong to the right class, then Yij hat is close to 1. And if you remember about how logarithms work, the logarithm of a value close to 1 is close to 0. And so we'd have 1 times 0 here, which would be 0. And that would be good because it would contribute nothing to our log loss, saying that, hey, we got this one right, we didn't do anything wrong. In reality, that predicted probability is probably not going to be exactly 1. It'll be close to 1, and then the logarithm of something close to 1 will be a relatively small negative number, and this will contribute something small to our log loss. If, however, our model is very certain very certain that our observation does not belong to the class that it actually does belong to. So it assigns a low probability for the actual class, for membership in that actual class. Then I'm taking the logarithm of a small value, something closer to 0 or a half, basically something further away from 1. And the further I get away from 1, the larger in magnitude that logarithm is going to be. So it's going to be a negative number that is perhaps quite large. The lower the probability I assign, the larger that logarithm will be, again in magnitude. So being relatively sure that my observation does not belong to the appropriate class really penalizes me. It contributes a lot to that logarithm loss. So for log loss, smaller numbers are better. This negative is out in front because all of these terms with the logarithm are going to be negative. So that sum will be a negative number. I'm going to multiply it by minus 1 over n to make the negative number positive. And then dividing by n will take the average. So the average log loss over each row in my data set, over each prediction that I made. So again, another performance metric. This performance metric cares not just about the classes that your model predicted each observation belonged to, but it cares about the certainty that your model had. Was it very certain that your model belonged to the right class? Good. Was your model fairly certain that your model didn't belong to the class that it actually belonged to? That's bad, and that will contribute again to the log loss and inflate that value. All right, I think that's plenty for now. I think we'll have questions about this, so bring those questions to class with you. We'll have plenty more time to talk about this multi-class log loss if that's something that you want to do. But for now, thanks for sticking with me through the video. Again, I hope it was useful. Please do play around within this notebook. Take a look at some of the other data sets. I'll see you next time. Bye.